Differential shock, like thermal shock, occurs in biphase systems. Differential shock can occur whenever steam and condensate flow in the same line, but at different velocities, such as in high-pressure condensate return lines. In biphase systems, the velocity of the steam is often 10 times the velocity of the liquid. If this gas flow causes condensate waves to rise and fill the pipe, a seal is formed with the pressure of the steam behind it. Since the steam cannot flow through the condensate seal, pressure drops on the downstream side. The condensate seal now becomes a piston that is accelerated downstream by virtue of this pressure differential. As it is driven downstream, the piston picks up more liquid that is added to the existing mass of the slug, and velocity increases. This is differential shock. If the slug gains high enough momentum and is then required to change direction at a T or elbow or is stopped by a valve, great damage can be done. In the demo lab at Armstrong International, we have assembled a fixture to illustrate the problem. We use this 20-foot, 2-inch diameter glass pipe to act as a condensate return line. The pipe is pitched 1/4 inch in 10 feet to provide gravity flow. Flowing through the pipe, we have cold water. In addition to water, we can also have compressed air flowing in the system to simulate flash steam flowing across the top of the condensate by virtue of differential pressure. One flow meter constantly measures the flow rate of the water. Another flow meter continuously monitors the flow rate of the compressed air. As you can see, we now have 1,500 pounds per hour of water flowing in our glass pipe, and no compressed air. Under this condition, our pipe is approximately half filled with water. As we increase the flow rate of water in our pipe to 2,000 pounds per hour, the depth of the water increases to 5/8. We now introduced compressed air into the system to simulate flash steam, with a flow rate of about 200 standard cubic feet per hour, and the depth of the water recedes. We are increasing the speed of the water flowing through the pipe by virtue of the velocity of the gas flowing across its surface. Observe now as the compressed airflow increases. The waves formed on the surface of the condensate become higher. Further increasing the airflow causes the waves to block off more of the cross-section of the piping until a seal is formed, completely closing off the pipe. A slug of condensate is accelerated downstream by the pressure differential, becoming a piston that gains in mass and velocity as it travels. The proper sizing and pitching of condensate lines are the only means of guarding against this type of problem.